Yeah, guys, very good afternoon. Are you able to see my screen, PPT, presentation slide?
Sir,
Yeah, it's still less number of students, even not at all joined 45 students. With just a couple of minutes, we recap, then we go to today content. Okay. I mean, I have been shared some videos, video links in the LMS. I hope that you might have been gone through that. So you can see that different types of bearings in original picture. You might have been seeing different types of bearings and corresponding applications. Anyway, we discussed yesterday, but you can get it more clarity in the video. I hope that. Okay. Now this is the we started yesterday rolling contact bearing. In the rolling contact bearing, just I go through that, just recap, just a couple of minutes. Still students are joining. Okay. Yeah, we discussed yesterday different types of bearings, deep groove, rolling contact bearing, basic principle of rolling contact bearing, and the construction design of bearings inner is because very important this in that the construction, then only able to understand further derivations, concept. Okay. Now this is, just I recap this construction principle, construction of the design of the bearing, then we will start today discussion. That will be better. Otherwise, you may not understand that this concept derivation. Okay. Now see here. This is inner ring. Now, okay, I take my pointer. This is inner ring. This is outer ring. This is inner outer corner radius. This is the inner corner radius. This is the bore diameter is equal to shaft diameter. This is outside diameter. Now, this is his face. Okay, this is outer ring, race, outer ring ball race. This one. Now, this is the separator. Okay, these are the content we discussed yesterday. Terminology. Now, I just recap. And radial ball bearing, radial ball bearing, thrust ball, radial ball bearing and thrust ball bearing. How the load is acting. We discussed. And we discussed this different types of bearing: deep groove ball bearing, cylindrical ball bearing, angular contact bearing, and sorry, self-aligning bearing. We discussed in the yesterday class, and spherical roller bearing, and taper roller bearing, and thrust ball bearing. Each one we discussed. Now today we move to these are the things yesterday we discussed. Today we done. Then this is the self-aligning bearing. We discuss here. This is the self-aligning bearing. How this, the bush made in the form of, say, spherical shape, how it will be self-aligned, we discussed. But without self-aligning, this is before the soft in strike condition. But during power transmission, due to some misalignment in that sense, there may be error in manufacturing. During manufacturing, there may be error in the hole diameter or shaft diameter. Then during the power transmission, then the bearing going to be like this. This corner of the bearing, this corner of the shaft are just going to be touch on the shaft, top side of the bush. Then bottoms of this journal, another edge is going to be touch on the bottom side of the bush. Then it will causes the it will causes or prevent the lubrication flow inside the journal and bearing, in between the bearing and journal. Hence the bearing is going to be, the journal going to be a failure. Would like to avoid that, we are using such a kind of bush, I mean spherical shape of bush we are using here. Then inside the bush the shaft is connected. Then small misalignment can be adjusted by this mechanism. Okay, that is principle of self-aligning bearing. Now, yesterday we discussed up to this and we have seen some of the bearing types. Now, today we are going to discuss selection of bearing type. Selection of bearing type. I mean, this is what are the how to select the bearings based on load, based on I mean, especially mainly load condition. Now, see here for low and medium radial loads, ball bearing is used. Whereas the heavy loads and large shaft diameter roller bearing is suggested. Okay, this is you may expect. I mean, one mark questions in any objectives, even competitive exam. Okay, self-aligning ball bearing and spherical roller bearing. I mean, self-aligning ball bearing, self-aligning spherical roller bearings are used in the application of misalignment between the axis and shaft. Yesterday we discussed here self-aligning ball bearing. Instead of self-aligning ball, we are using instead of self-aligning ball bearing, you are using instead of ball, we are using spherical roller ball, spherical roller. Hence, the self-aligning bearings, we can self-aligning rolling bearing, we can classify into two types. One is self-aligning ball bearing, self-aligning spherical roller bearing. Where we are using misalignment between the axis of the shaft and housing or bush. I mean, axis between the shaft, housing, or bearing. Okay, so those places. Thrust ball bearing, where we are using thrust ball bearing. Thrust ball bearing is the medium thrust loads wherever the heavy thrust loads, cylindrical roller bearing. I mean, thrust ball bearing can be used in medium thrust loads, but heavy thrust loads, we have to use the cylindrical roller bearing. We have to use cylindrical roller bearing. It's simple theory. It's not difficult one. Okay. I mean, for medium thrust loads, we have to use thrust ball bearing. For heavy thrust loads, we have to use cylindrical roller bearing. Okay. Now, when we are using double thrust bearing, it can carry the thrust load either direction. Double thrust bearing means you might have been seen herringbone gears, right? Herringbone gears. This is the in the single in the single cylindrical disc. In the single cylindrical disc, two sides the helix can be helix angle can be made. Now I draw it now for the front view of this. Now this is the shaft, right? We already discussed this uh, I mean this gear, herringbone gear. This is like this. The teeth are like this. The teeth are like this. So why we are using this type of herringbone gears? The axial thrust going to be balanced because balanced this kind of design. Because this teeth, half of the teeth in one direction, half of the teeth compared to this opposite direction, helix angle. Hence, the thrust force, the thrust axial force will be balanced this kind of teeth. Similarly, if the double acting thrust bearing can carry the thrust loads in either direction. Okay, thrust loads can be either direction. I show you here double acting thrust bearing. Double acting thrust bearings here. We already discussed this one thrust bearing. Here only we are using single roller. Suppose in this in this double roll, suppose here only single row balls we are using here. Now in this case, single row balls we are using. Perhaps if we are using double roll balls, it will be better for axial thrust, axial load condition. It will be much we can use for more load carrying capacity, more axial load condition. we can use this type of design using two rows of bearing. Now in this construction, whatever now I am showing that it is only one row of balls. If suppose we use two row of balls, then it will be, I mean, the load, whatever the actual load, it will be easily observed, easily. I mean, maximum axial load can be observed, can be withstand such a kind of design. Now, okay. Now for high speed application, deep groove ball bearing is better one. Deep groove ball bearing and angular contact bearing, because deep groove ball bearing, here this is the ball bearing. I mean, here the ball or point contact, it's not a line contact, and the amount of heat generation inside the ball bearing is less as compared to line contact, or else as compared to surface contact. I mean, surface contact in that sense where we discussed journal bearing, those places more heat is generated. I mean, ball bearing heat generation is less than the roller bearing. Roller bearing heat generation is less than the journal bearing. Okay, so then the temperature rise can be avoided, hence it can be more speed can be obtained using deep groove ball bearings and angular contact bearings. But for high speed application, but heat generated more in deep groove ball bearings. Okay. Now this is the selection of ball bearing based on load condition, based on radial load, based on axial load or thrust load, based on self-aligning, third point, and based on speed, based on speed. I mean, high speed applications, deep groove ball bearings, first option. Second option is angular contact bearing. Third option is cylindrical roller bearing. Cylindrical roller, I mean, roller contact bearing. Okay, third option. Okay, but in most of the applications we are using deep groove ball bearings. Now I come to this Strybacks equation now, and static load carrying capacity, static load carrying capacity of the bearing. See, before entering into that, some more points. Yeah. Now, 1 minute, please. Yeah. Now, which bearing is high rigidity? Line contact bearing or roller contact? I mean, roller bearing is more rigidity or ball bearing is more rigidity? You please tell me that. Which bearing is more rigidity? Roller bearing or ball bearing? Yeah, please. Someone reflect. Which bearing is more rigidity? Okay.
Roller bearing maybe, sir.
Okay. Any reason? More rigidity. Yeah, you are correct. So tell me. More rigidity, roller bearing. Okay, good. And any reason? And I mean, roller bearing is more rigidity or journal bearing is more rigidity?
Roller, sir.
Eh?
Roller bearing is more rigidity, sir.
Okay, I am comparing now. I am comparing journal bearing. Okay, I tell you the reason. I mean, I tell the condition. Roller bearing and journal bearing. Journal bearing is like boundary lubrication, because boundary lubrication, which what example? IC engine, right? Then which one is more rigidity? Roller bearing or journal bearing? I give you a clue. See, wherever
Journal bearing, sir.
which one, ma?
Journal bearing, sir.
Yes, because wherever more surface contact, the rigidity will be more, right? If you take ball bearing, the line point contact. If you take roller bearing, it's a line contact. If you take our boundary lubrication in journal bearing, it's a surface contact in more rigidity. Okay, okay, that's what. And which bearing will be more noise? I mean, can you tell me the order of the noise? Roller bearing is greater than the uh, greater than the line. I mean, ball bearing. Ball bearing is greater than the journal bearing. Is it right? Noise, more noise. But based on comfortness and based on our requirement, we have to use for only. I mean, journal bearing is more rigidity and roller bearing is more rigidity. Hence, I cannot use roller bearing, ball bearing. We can't say that. Based on our condition, based on our requirement, we have to use that bearing. Now, I'm asking that which one is more nice, roller bearing or ball bearing or journal bearing?
Sir, can you repeat the question?
Which bearing will be created more noise? Can you tell
Sir,
me the
roller, sir.
order? Journal bearing, ball bearing, and roller bearing. Can you tell me the order of more noise in these bearings? Simple question, pa. I'm asking simple questions only. Yeah, please, someone come forward. I don't know nowadays how many students are there. I am because last two classes I didn't see the students, number of students.
Sir, roller bearing, then ball bearing, then journal bearing, sir.
Roller bearing, then ball bearing. Oh, you are saying like this? Are you saying like this? Yeah, I write it.
Decreasing order of noise creation, sir.
Increasing. First, you are saying roller bearing. Am I correct?
Yes, sir.
uh, I think wrong. Just you think. See, I told you that based on contact, metal to metal contact, you can define that. No, which one is more less contact? Ball bearing is point contact. Hence, will it develop more noise? When the two surfaces are going to be in contact while dynamic condition, then more noise will be generated. Hence, which one is now? Ball bearing is generate more noise. Now you might have been understood. Ball bearing is, I mean,
Sir, but
journal
roller
bearing.
content is line content, na, sir.
Yes,
Line contact.
yeah. Now journal bearing boundary at the boundary lubrication. Then journal bearing is more noise. Correct? Then because this is surface contact, more region of interest, while in the fixed component the journal is rotates inside the journal rotates inside the bearing, then more contact will be more noise, more contact surface, more surface contact. Now roller bearing, line contact with other component like a fixed component, stationary component. It's stationary component in the sense the bearing, okay, or casing or roller. So I mean inner race or outer race, right? Then this guy roller bearing is a line contact, hence obviously less noise as compared to journal bearing. Now R is greater than ball bearing. Ball bearing is point contact only, hence obviously the noise is going to be less. Noise going to be less. Then this is going to be a smooth functioning also. Ball bearing will be a smooth functioning, less noise. start to 1 minute. How many students are there? Yeah, Kalyan, please send a WhatsApp message. Only 52 students are there.
Yes, sir. I already informed, sir. Once again, I will inform.
Yeah. Okay. Now I come to this. Now we are going to discuss about the static load carrying capacity of the bearing, static load carrying capacity, and the dynamic load carrying capacity. Okay. Now, when the static load is presented in the bearing, I mean static load. When the static load is presented in the bearing, I mean, you very well, very simple question, no? A very simple question. Static load is defined as the load acting on the bearing when the shaft is stationary. When the shaft is stationary means when the shaft is connected, the shaft is not a rotation. During that time, the shaft is not rotates. Hence, ideally, obviously, it's a static load, right? Now, I mean, when the static load presents, it will produce the permanent deformation. Permanent deformation in the balls as well as, now I take this. Now this is shaft is connected here. Okay, shaft is connected here. Obviously, when the shaft is not rotates, I mean not rotates, then static load will be presented. Then that static load will develop the permanent deformation of balls and races. Where the balls and races are presented? Balls and races are presented here. Now, this is the balls and races are presented here, right? This is a ball, this is inner race, this is inner race, this is outer race. Obviously, this is going to be subjected into static, I mean permanent deformation when the load when this is not rotation, the shaft is not rotation, right? Now, the total permanent deformation going to be 0.001 times 0.0001 into d. This is the total permanent deformation 0.0001 in 1 of the 1 into d. D is the ball diameter or roller diameter occurring at the most heavily stressed ball. this is the this is the maximum deformation condition. The value, the empirical relation 0.00001 is, I mean d 0001 into d 0.0001 into d. They might have been studied in the theoretical as well as practical conditions. Then they declared that this is at heavily stressed ball load condition. Heavily stressed load condition in that sense, when the ball is subjected into heavy stress, when the roller is subjected into heavy stresses, this is the maximum permanent allowable, I mean maximum deflection, maximum deformation occurred in the inner race in the inner race of the contact. Okay, now I mean, even though, I mean, this is, I mean, inner race of the contact and it can be tolerated practical condition, but without any disturbance like noise and vibration. Up to this deformation only allowable. Beyond that, the deformation will be more than this, then it will be a noise, it will be a more noise, it will be a more vibration. Okay. Please keep in mind, this is the relation we are going to use in our problem while solving the problem. Okay. Now the value of static load carrying capacities are directly given in the directly it can be given. The value of static load carrying capacity, it will be given in our design table or this manufacturer catalog. Okay, we can take it from there. Okay, that is based, I mean, we can take it from the table or design manufacturer catalog. Okay. Now, where the values are minimum, I mean, where the values are minimum or the extreme smoothness operation can be obtained. The deformation value will be minimum, then extreme smoothness operation can be obtained. When this deformation value is minimum, less than this assigned value point, this equation, then it will be a smooth operation can be obtained. Okay. So just briefly, I tell you that static load means that soft in static condition. Now, the second point is deformation of balls and races is proportional to increment of load. Now, when the radial load is acting here, now which portion of the balls are going to subjected into deformation? Which portion of the balls subjected into deformation? Please, someone tell me that.
Bottom.
Yeah, bottom portion of the balls are going to subjected into more deformation. Bottom portion of the balls as well as rays, right? As well rays are going to be subjected into, this is a load. This is the load C naught. I'm putting the load C naught. This is the rays. This inner rays, balls going to be subjected to the outer rays, and balls are going to be subjected into deformation. So in our static load carrying capacity discussion, we are going to consider the bottom portion of the ball. Bottom portion of the ball only we are going to consider. Okay. And at worst case, most heavily stressed ball, the permanent deformation maximum going to be allowable up to this only 0.0001 into d is the diameter of the ball. Now, now we discuss about static load carrying capacity equation. How to find out the static load carrying capacity? I mean, the guy developed the Strebach's equation, that is called the Strebach's equation. Who developed the concept, right? His name is Strebach. He developed the concept and the equation static for finding the roller bearing static load carrying capacity. So in his concept, in his development, he followed some assumptions. He followed some assumptions. In this assumptions, the first assumption he considered, the races are rigid and retain their circular shape. I mean, the races are rigid and retain the circular shape. Circular shape in that sense, what we consider in the beam theory. Can you tell me that in the beam theory, what is the beam theory? One important assumption. Yeah, please. What is the important assumption in the beam theory? The material is homogeneous, right? The load should be acting perpendicular to the axis of the beam, right? Second assumption. Any other? What is the third assumption? Important assumption. Very simple question, pa. You wrote a GATE exam, na? What is beam theory? This is a neutral layer, right? Neutral layer going to be any stress going to be presented. The neutral layer, zero stress, right? Hence, whenever the load is acting before plane, the beam should be plane before loading. The beam should be plane after loading. Am I right or wrong? Arey, have you studied or not, pa? Beam theory? Hello?
Yes, sir.
Yes. Similarly, he considered in his assumption, the first assumption, the races are rigid and retain their circular shape. In his assumption, he considered. Okay. And the balls are equally spaced. Whatever we consider the bottom row balls only, top row, when the load is C naught is acting here, the top row balls, I mean, I mean, above the bearing top row balls are not subjected to any load. Only bottom row balls we consider for in our for in this sorry in this in this concept in this development. Okay, the balls in the upper half do not support any load. That is also one assumption. These assumptions are very simple. Now we come to this. Now see the forces are acting in the inner race through the rolling element. I erase some other things. Okay, now, yeah, the forces are acting on the inner race through the rolling element, which is support the static load, C naught. Now, see here, the C naught is acting through the row of balls P1, P2, P3. Now, this ball is subjected to direct radial load. Straight direct radial load. This ball is, I mean, what is the assumption? Each ball is positioned equal angle, and this is the ball 2 is positioned here at beta angle. Ball 3 is positioned here at beta angle. Then what is this angle? Now this is a 2 beta. 2 beta. Now this is information required. Now based on the load acting on the balls, I would like to find out what is the C naught. What is my radial? I mean, what is my static load condition now? Now see here, this is a ball P1. Here, this is a ball 1 is direct load P1, right? Now ball here, ball 2. Take ball 2 here. Now what is this? I mean, see this is, come here. This is ball P1 1 is here, ball 2 is here, ball 3 is here. This is symmetric, ball 2, ball 3 here. Now C naught is equal to P1 plus, this is the load P1 here. What is the load acting here? This load. Now this is 2P2 into cos beta, right? 2P2 into cos beta here. This ball subjected into load to P2 into cos beta only, but here this is ball 2. There is a 2 balls, hence we are multiplying 2 into P2 into cos beta. Now I come to the ball 3. Ball 3, P3 into cos 2 beta, because already we know this is the 2 beta angle. 2 beta angle. Hence P3 into cos 2 beta. For the where the load is acting in ball 3, acting load is P3 into cos 2 beta. Then here on ball ball 3s are identical, I mean symmetric, and 2 P3 into cos 2 beta. What about ball 4? Can you tell me there? What about ball 4 here? Ball 4. If I add ball, yeah, please don't waste time. Please, can you tell me that? What is the ball 4 load here? Next component.
2p4 cos 3 beta, sir.
Yeah, thank you. Thank you. But 2p4 cos 3 beta. Okay. Sometimes, whenever we are going to discuss that also, how many balls going to be used in the roller bearing? That also table has been given to us. Whenever we are considering only 6 balls, in the 6 balls are symmetric side, hence we are considering this. Up to this we are considering when the balls are going to be increased, then this is going to be considered. Now see here, I would like to ask one question. Suppose I am taking ball here, this ball. Now what is the load going to be here in this ball? Can I neglect it or can I consider? For our understanding, I asked you questions at ball 4. What is the load? You have been reflected 2p4 into cos 3 beta. Very nice. But when I am coming this direction, I am adding number of balls in the direction. When I am coming to this axis, is it considered the load? When I am coming to this position, especially this position?
We can neglect, I think, sir.
Yeah, we can neglect. Exactly. Thank you. Nice. Okay, because the beta is 90. hence this is going to be 0 and it will be neglected. Okay, now this is the thing. Now this is I mean, as the race and as the races are rigid, only balls are deformed here. As the races are rigid, only balls are deformed here. Balls deformed here. Suppose delta 1 and deformation at most heavily stressed ball is 1 only. Most heavily stressed ball 1. I mean, this is the things you can understand. I no need to explain this. Heavy stress is in subjected into ball 1 only. Okay, I mean, due to this deformation, the inner race is deflected with respect to the outer race. Now, I mean, during this deformation, I mean, that ball, this is the original before deformation, this is after deformation, this is before deformation, this is before deformation, this roll, this circle, this is the inner race after deformation, after deformation. Okay, after deformation. Now we are saying that now we are considering deformation of the ball. Now deformation of the ball here for one ball, one is d1, this is the d1. So ball 1 is d1, ball here also d1. How can I find out d, how can I find out d delta 2? Now this is a rectangle triangle, right? I'm taking this rectangle triangle, this one I'm taking this one only, this rectangle triangle, right? Now this is 90°, now this is 90°, this is already we know delta 1. Now what is this? This is we have to find out this only. Okay, now what is delta 1 here? Now delta 1 by delta 2. This is we know the angle beta, right? Now this is our delta 2, right? Now delta 2 divided by delta 1 is equal to cos beta. Now from this we are able to find out delta 2 is equal to delta 1 into cos beta. Cos beta. Okay. Now, now we move to the further. I mean, further further derivation. Now, yeah. Now this is now the static load carrying capacity of bearing is defined as the static load which correspond to the total permanent deformation. Whatever we already told you that permanent deformation of the balls and ratios at most heavily stressed point of contact, that is equal to, I mean, that is equal to 0.001 times of ball diameter. Okay. Now after deformation, this is the original condition before deformation at O origin. Now after deformation O to O dash, based on that deflection we are considering, now we are able to find out the delta 2 and delta 1. Now delta 2 is equal to this delta 1 into cos beta, right? Now, I mean, we are not going to discuss a Hertz equation. Based on the Hertz equation, they are considering that delta proportional p power 2 by 3. They might have been gone through some research and they might have been published some journal paper. So directly they have taken it and they kept it in our book. Okay, hence delta is proportional to p power 2 by 3. Now delta proportional, I would like to remove the proportional, then I am introducing C1. Then delta 1 is equal to P1 into 2, P1 power 2 by 3. Suppose delta 2 proportional to P2 power 2 by 3, then I remove the proportional, then I am introducing C1, delta 2 is equal to C2 into P2 power 2 by 3. Now from these relations I am able to find out delta 2 by delta 1 is equal to this relation. Now delta 2 by delta 1 is equal to, from this relation, this one, from this relation, we have found delta 2 by delta 1 is equal to P2 by P1 whole power 2 by 3. Now see here, this is equation already we discussed B. This equation based on this our Hertz equation. Now simplify this equation B and C. Finally, we are getting P2 by P1 whole power 2 by 3 is equal to cos beta. Then P1 is P2 is equal to P1 into cos beta whole power 3 by 2. Right? Similar, I mean, now from this relation, from this, solve this, simplify this equation B and C, finally getting P2 by P1 whole power 2 by 3 is equal to cos beta. Now, from this relation, we are able to find out P2 is equal to, we know P1 because direct load is acting, right? P1 we know. Here, P1 is maximum load, P1 is maximum load, and P1 into cos beta whole power 3 by 2. Now, what is a P3? P3 is also going to be P1 into cos 2 beta. Here beta, here cos 2 beta. As I told you earlier, when you go for bearing, ball 3 or 4. When you go for ball 4, it will be 3 beta. Now, this is ball 3. Okay, now then substitute these values in our original equation, whatever we discussed. This is in the C naught equation, then you are going to get this equation finally. This is the substitute our P1 is P1 only, P2 in terms of P1, P3 in terms of P1, substitute in our original equation, whatever we discussed earlier, and finally we are getting this equation. Then this equation, this is a constant, 1 plus 2 cos beta whole power 5 by 2 plus 2 cos 2 beta whole power 5 by 2, this constant. Now we are assuming that the simple notation, m, whatever I am saying here, this only. This term I am considering in terms of m. Now this is our C naught is equal to P1 into m. Now C naught is nothing but our static load carrying capacity. Now further we have to simplify that. Now earlier we didn't consider how many number of balls. Now m is now this is m, right? This whatever this is terminology going to m. Now how many balls? But one assumption is the balls are equally distributed, equally positioned, or equally oriented along the circumference direction of the bearing. Hence now beta is equal to, it's a generally you can easily understand, 360 divided by number of balls. 360 divided by number of balls. Now, right? Now this is the balls. For Z is number of balls 8, 10, 12, 15. Please carefully listen here. Now I am taking number of balls 8, 10, 12, 15. Like that I am taking. Okay. Now number of balls here, m value I am getting 1 point. When I am taking 8, 10, 12, 15. Now I come to this. Now I am taking 8. Now 360 divided by 8. Later substitute this beta, now we know, substitute this equation. Now second case I am taking number of balls 10, then beta, now beta is equal to 360 by 10, right? Third case number of balls 12, 360 by beta is equal to 360 by 12. Then each case substitute the values. Each, suppose for example you take beta 1, beta 2, beta 3, like that. Substitute our m equation. Then finally at each case we are getting the values going to be like this: 1.84, 2.28, 2.275, 3.47. This is m value we obtained from the equation E. Now take Z by m, what is the value? Now we know number of balls 8. Now m value we know. Now substitute this m value we know. We know m value. Already we have found this. Here m, this corresponding to 12 balls, corresponding to 15 balls. Then now you find out Z by m ratio, capital Z by m ratio, this one. Number of balls divided by m. 8 by 1.84 is given 4.35. 10 by 2.28 given 4.38. Similarly 12 balls. 12 by 2.75 given 4.36. Similarly, 15 balls, 15 divided by 3.47 given 4.37. I mean, always the Z by M ratio doesn't change. Almost same. Hence, the guy Stryback finally considered that, I mean, whole value 5. That is very, very important. Based on this, based on his concept, he came to final conclusion. This Z by M value we can assume that 5, because all the values close to each one is all the values same, almost same, 4.36, 4.35, 4.37, 4.38. Hence, finally he suggested that the Z by ratio M we can take 5. Hence, finally Z by M is equal to 5. Z by M is equal to 5. Then M is equal to 1 by 5 into Z. Now again substitute in this equation. Now this is our equation, right? C naught is equal to P1 into M. Then and then the M in terms of Z I would like to submit, because M value we know now 1 by 5 into Z. Z is nothing but number of balls. Now because we can't measure beta value oftenly, hence now number of balls we know. Based on that, finally he came to know that he came to conclusion 1 by 5 into Z into P1. This is the load. Now further, I mean, as per the experimental, from the experimental evidence, from the experimental, he might have been conducted experiments, then he found that force P1 required to produce, given a permanent deformation of the ball, here now P1 is equal to K into D squared. Now this is nothing but just I mean, this is not exactly one. For your understanding, I am going to give some this thing. I mean, what is the stress? I mean, the ball 1 is directly subjected to load, maximum load. Now P1 divided by A is equal to strain, right? Young's modulus into strain, right? Young's modulus into strain. Now P1 is equal to pi by 4 d squared and E into epsilon. Now these are the things are constant. Now these are the things constant. Now P1 is equal to K into D squared, he considered like this. Okay, that's what here he declared that D is a ball diameter. Now I am here. That D is the ball diameter, and F and the factor K depends on the radii of the curvature of the point of contact, and also moduli of the elastic material. That's what moduli of the elastic material from this. Now finally, from this equation G and F, substitute P1 value here. I mean P1 value here. Then I mean, from the experimental evidence we are considering this information, P1 is equal to K into D squared. Then substitute here, that is our final equation. C naught is equal to K into D squared into Z by 5. This is a Stryback's equation. I mean, C naught is nothing but our static load carrying capacity of the ball bearing. Now, are you clear? Any doubt, please? Hello? Yeah, please, someone reflect upon.
Clear, sir.
No, sir.
Okay, now I come to the equivalent bearing load. I mean, see here, in actual condition, in practical conditions or practical application, the force acting in the bearings, there are two components we discussed already. What are the two components? One is radial component, right? And axial component. Radial component, axial component. It is there. I mean, these two components converted into single hypothetical load, because when we are going to find out the dynamic load, these two components, this radial component and axial component, will be converted into single hypothetical load. That hypothetical load fulfilling our dynamic load carrying capacity. When we are going to convert it into single hypothetical load using these two values, that hypothetical load must fulfill our dynamic load carrying capacity. That's what here we are considering here. Then, but one assumption, what assumption we are considering here, the equivalent dynamic load is defined the constant radial load in radial bearings, constant radial load in radial bearings, or thrust load in thrust bearings, but which applied in the bearing it will give same life. It means that now see here, this is the bearing. Now bearing is subjected to radial load. During that time, the bearing is life is maybe for 200 million of revolution. Suppose the bearing, now the bearing is subjected to radial load. Suppose the bearing is subjected to, now the bearing is going to subjected to axial load, then this is FA. At that time also the bearing should satisfy, the bearing will give the same life of the same life, same 200 millions of revolution, right? So that's what they considered in this. That's what the thrust load in bearings which applied the bearing, it would give the same life of the bearing. This is based on this condition they are utilizing this. This is our equivalent, this is our equivalent dynamic load. P is nothing but equivalent dynamic load. Here X is our load factor. Okay, V is nothing but race rotation factor, and Fr is our radial load, and Fy is load factor, axial load factor or thrust load factor. Here X is radial load factor, Y is axial load or thrust load factor, Fa is radial axial load. But why we here also the V is nothing but race rotation factor, outer or inner, because where the radial load is involved, that place only we have to use race rotation factor, because this is depends on radial load. The rotation of the bearing with respect to directly related to radial load. Rotation of the bearing, rotation of the inner space, inner race or outer race. Inner race, outer race in that sense. Suppose I am fixing this inner race, I am rotating outer race. Suppose I am fixing outer race on the structure, I am rotating the inner race. Hence, the radial load, when we are considering radial load, that rotation factor will be involved in the radial load only. It's not in the axial load. Hence, we are considering this race rotation factor along with the radial load. Okay. Now come to here. Now X and Y are the radial and thrust factors. Now suppose V is equal to 1. What is when it will V is equal to 1? When V is equal to 1 during that time, while the inner race rotates, outer race is stationary. While outer race is rotates, outer race is rotating, inner race is fixed. Okay, inner race is fixed. Then now what is this? V is equal to 1.2. In V is equal to 1.2, we have to consider. Okay, now during that time, in this case, inner race is stationary. Inner race is fixed with the shaft or some other structure. Okay, outer race will be rotates. Now in this case, but most of the applications we are using this ball bearing. Inner race is rotates, outer race is fixed. Whatever we have shown in the first slide one diagram. Okay. Now when we consider such a way that our equivalent dynamic load carrying capacity, equivalent dynamic load carrying capacity is equal to X into Fr plus Y into Fa. Now suppose pure radial load, then pure radial load X into Fr. Okay, pure radial load, the dynamic load carrying capacity is equal to equivalent dynamic load carrying capacity is equal to X into Fr. Now pure axial load, then during that time, X into Y into Fa, Y into Fa. Okay, now I come to this some more analysis. Then now we have been discussed static load carrying capacity, dynamic load carrying capacity. Okay, now I mean few more points about the dynamic load carrying capacity. The ball bearing, the life of ball bearing. Yeah, tell me, ba. Hello. Any doubt?
Sir, time is already 3 o'clock, sir. We have another class at 3.
Okay, then I stop it. Okay. Yeah, yeah. Please, this is the theory. Go through this. Next class we will discuss just 5 to 10 minutes about this load life relationship. Then we move to the problem in the next class. Yeah, I come to the main screen. Please wait. How many of them there? Only 56 students only. Kalyan. Hello, Kalyan, are you there in the meeting? Hello. Kalyan, are you there? Please, someone reflect, guys. Actually, today I had some other commitments. That's what I took. I started a class 2 o'clock. But actually, our regular time is 1:45 only. Okay, sorry for that. Okay. Okay, please. Do you have any doubts?
No, sir.
Yep. Okay. Thank you. So today evening 6:15 you are going to have exam. Yeah, please prepare well. Wish you all the best. And numerical questions also there, and the theory questions are simple questions only. Don't waste time in the theory questions. So move to numerical questions. Numerical questions also you're able to solve within minutes. Such a kind of questions only we have prepared, and we have prepared our minor one. Okay, guys. I think the next class, next class, we try to complete this chapter. Okay, we may consider up to this chapter for our mid exam. Okay, guys, thank you. Okay.
Thank you,
Kalyan,
sir.
are you? Thank you, pa. Thank you. Kalyan, are you there in the meeting? I think he is there in the meeting. Why he is not speaking?
There.
Yeah, tomorrow. When is our CRC meeting?
And this week we will have.
Yes. Anyway, we are going right speed. We have enough time. Okay. So slowly, I mean, we have enough time. Anyway, before mid, we try to finish this chapter. Then after mid, we are going to have more time. Then we can complete chapter another 2 chapters. Then if we have a more some time, we can go for some one or two at least 1 or 2 classes. At least 2 classes I will arrange for our discussion from chapter 1 to end. We will discuss even 2 classes or 3 classes, doesn't matter. Okay. Okay, guys, thank you. I'm closing the meeting, Kalyan.